Turning on a switch. I didn't actually watch this video. And the gene is going to be expressed because we make the mRNA. So we call this gene expression when we make the protein. All right, so as shown in that last video, about 2% of our DNA is coding. The rest has other purposes, or perhaps is still considered junk DNA. If we change a single nucleotide, that might be due to a mutation. It may not cause a disease or anything, but the only thing we really talk about mutations are in your homework. But we're going to be working with these things called SNPs, single nucleotide polymorphism, where a nucleotide in a population, that particular nucleotide is different in different people, or different animals, whatever. So again, I'm just giving you a little bit of background here to lead up into some stuff we're going to be doing in a few days. But a SNP, if it's in a coding region, that may or may not have an effect on a protein. That's most likely to have an effect on a protein. If you have a different, just like a mutation essentially, right? If you have a different nucleotide, it's a good possibility that that person has some different trait than some of the different nucleotides on that same spot. If it's in a junk DNA, it's not going to make any difference. I'm just calling junk DNA. If it's in, it might have a major effect if it's in regulatory DNA. So last thing I want to show you a couple of videos here of why regulatory DNA might matter. This is just a terrible quality, yeah.
So what do we learn by looking at 600 million years of animal history? Evolution's tinkering with mammalness to make whales. In the same way, it's tinkering with fishiness to make tetrapods. And it's tinkering with animalness to make all the different body plans that we see. All these different creatures are variations of the same theme, restated over and over again. The question was, what was evolution tinkering with? One of the remarkable discoveries of the last 20 years is that evolution is not tinkering with the bodies. It's tinkering with the recipe, the machinery that builds bodies. What is that recipe? What is that machinery? It's the genes.
Scientists had long suspected that embryos held clues to how animals evolved. All embryos.
Think about this. What's the first thing you can remember about your life? Nicholas, what's the earliest thing you remember in your life?
I think I was in a playpen and my mother was on the phone.
Oh. How old were you?
I think 17.
17? This is like last night. This is the last thing I remember.
No, it was probably like, two.
That's pretty young, isn't it?
Yeah.
Yeah. How about anybody earlier? Earlier memories? Think back, come on, think back. You were 2. That you may have learned them because your mother tells you stories or something. Yeah. Well, our memories change too. We readjust our memories. Yeah. Yes. Our brains are bad for that. But come on, think back. Trevor, you can probably remember. You remember being born, don't you? And even before that, think back.
Before you were
Yeah,
born.
before you were born. Trevor's story, he was telling me this the other day. You remember when he was a single cell. Single cell. Yeah. And then what happened to Trevor? He divided into 2 cells, right? And all those cells have the exact same DNA, don't they? And those 2 cells divide into 4, and into 8, and into 16. And they're all the same in the beginning, aren't they? Every cell is identical. But some of Trevor's cells had to become liver, and some had to become muscle, some had to become an eye, some had to become a heart, some had to become blood cells. They all have the same DNA. So how does that happen? Well, regulatory issues, right? Which genes get turned on? Does the liver genes get turned on, or do the heart genes get turned on? Muscle cells or something, right? So we have to regulate this somehow. which genes get turned on and off. So I want to show you a little bit more about that. And that's kind of what they're talking about here. They're talking about it in the context of evolution, how do things change. And the embryo is a great place, right? Because a little bit of change early on could mean a lot of change later.
Start out as clusters of nearly identical cells. But soon, the embryo partitions itself into specialized segments, which develop into the final form of the animal. What controlled this process? How did the embryos know what shape to take? One researcher, Dr. Ed Lewis of Caltech, studied this question for 30 years by crossbreeding thousands of flies. Lewis's work led him to a controversial idea. He proposed that a surprisingly simple mechanism was shaping embryos. He wrote that each segment of the fly was being directed to grow by a single gene. A small set of genes, a kind of genetic toolkit, appeared to be laying out the entire body. In 1994, Walter Gehring of the University of Basel isolated the gene that triggered the growth of eyes in fruit flies. The gene was called eyeless, because flies without it developed with no eyes. Gehring knew of a gene in mice that worked in the same way. He wondered, were the two genes the same?
And this question we tested by taking the mouse gene and putting it into fruit flies to see whether flies can understand the message of the mouse.
Gehring replaced a fly's gene for eyes with the mouse gene.
And to everybody's surprise, the mouse gene works perfectly well and can induce a compound eye in the fruit fly.
The fruit fly grew normal fruit fly eyes using a gene from a mouse. Not only did the two creatures use the same mechanism, they used the same gene.
So what this means is in some ways, some sense, evolution is a simpler process than we first thought. When you think about all of the diversity of forms out there, we first believed this would involve all sorts of novel creations, starting from scratch, again and again and again. We now understand that no, that